Every teacher you ever had told you the same thing about gravity. It is a force, and it pulls en masse. The heavier something is, the harder gravity grips it. But here is the part they left out. Light has no mass at all. None. The best measurements ever made pin its weight below a number so small it might as well be nothing. And by the law you were taught, a force that pulls en masse should have nothing to pull on when there is no mass there. A beam of starlight should sail past the sun without flinching, except it doesn't. Starlight grazing the sun bends by 1 3/4 arc seconds. Whole galaxies bend the light of galaxies behind them into rings. Black holes wrap light into circles and swallow it whole. The most massive objects in the universe do not ignore light, they command it. Which means the gentle little story you were handed as a child, gravity, a force, pulling en masse, may be hiding a lie about what gravity truly is. Settle in and hit subscribe if you are new here, because by the end of this, the straight line of light reaching your eyes will never feel quite so trustworthy again, and gravity will stop being a force and become something far stranger. Now, let's slowly ease into this. Part 1. The law that forbids what the sky shows. Somewhere very early in your life, someone taught you what gravity is, and they almost certainly got it wrong. They told you it is a force. They told you it pulls. They probably held up a pen and let it drop, and said that the earth was reaching up and grabbing it, tugging it down to the floor. And then, if you stayed in school long enough, you met the equation that seemed to make it official. The force of gravity, it said, is the gravitational constant multiplied by one mass multiplied by a second mass divided by the square of the distance between them. Two masses multiplied together, sitting right there on top of the fraction. The earth and the pen, the sun and a planet. The more mass, the stronger the grip. It is one of the cleanest, most powerful ideas any human being has ever written down, and Isaac Newton set it loose on the world in 1687. For more than 200 years, that equation was almost untouchable. It predicted the return of comets to the day. It steered ships across oceans by the positions of the moon and the planets. When the planet Uranus wandered slightly off the path the equation predicted, astronomers did not doubt the equation. They used it to calculate where an unseen planet must be hiding, pointed their telescopes at that exact spot in the sky, and found Neptune sitting almost precisely where Newton's law said it had to be. That is the kind of success we are talking about. Not a rough guide. The most accurate description of the physical world that had ever existed. But hidden inside that triumph, like a single loose thread in an enormous tapestry, there is a quiet little prediction that almost nobody ever stops to notice. Look again at the equation. The strength of gravity depends on mass. Two masses multiplied. And multiplication has a ruthless property. If either of those masses is zero, then the whole thing collapses to nothing, because anything multiplied by zero is zero. So Newton's law contains a very specific claim about anything that has no mass. It says gravity should not touch it. No mass, no pull. A massless thing, according to the most successful equation in the history of science, should drift through the universe completely deaf to gravity, ignoring even the heaviest objects, as though they were not there at all. And now we have a problem, because there is something in the universe that has no mass. You are bathed in it right now. It is pouring out of every lamp in the room and streaming down from every star in the sky. It is light. Light, as far as anyone has ever been able to measure, has no mass whatsoever. We will come back to just how carefully that has been checked, because it matters enormously, but hold on to the simple version for now. A particle of light, a photon, weighs nothing. It has no mass for gravity to grip, and so, by the plain reading of the law that most of us were handed in school, a beam of starlight skimming past the sun, should sail by in a perfectly straight line, utterly indifferent to the most massive object for light years in any direction. The sun should be to a passing beam of light as if it were not there, except that it is not. That is the whole problem. Starlight that grazes the edge of the sun does not travel in a straight line. It bends. The amount is tiny, far too small to notice with your eye, but it is real, it is measurable, and we have measured it more times than almost any other prediction in physics. And it does not stop with our sun. Out in the wider universe, entire galaxies bend the light of more distant galaxies that lie behind them, smearing their images into long curved arcs, into rings, into multiple copies of the same object scattered around the sky like reflections in a funhouse mirror. Whole clusters of galaxies act as enormous natural lenses, and astronomers now deliberately point their best telescopes through them to see things that would otherwise be too faint and too far to detect. And then there are black holes, where light is bent so violently that it can be wrapped into a complete circle, forced to orbit, and finally, past a certain boundary, swallowed entirely, never to leave. So look at what the universe is actually telling us. The most massive, the most extreme, the most overwhelming objects that exist do not ignore light. They command it, they bend it, they herd it, they trap it. The thing that Newton's law says should be immune to gravity turns out to be one of the things gravity acts on most spectacularly. This is not a small discrepancy to be smoothed over with a footnote. This is the single most successful equation in the history of science, making a clear, confident, unambiguous prediction about the night sky and the night sky flatly refusing to obey. I want to be fair to Newton here, because the situation is more delicate than a simple right or wrong, and the subtlety is where the whole story turns. It would be one thing if Newton's law had no idea what to do with light at all, if it simply threw up its hands. But that is not quite what happens, and the truth is far more interesting. When you push Newton's physics carefully, in a way Newton himself half anticipated, it actually does predict that light should bend. It just predicts the wrong amount. It gets close, tantalizingly close, and then falls short by a very specific factor, and that near miss turns out to matter more than an outright failure ever could. A theory that is completely wrong tells you to throw it away and start over. A theory that is exactly half right, that captures part of the effect and misses the rest by a clean, simple ratio, is doing something stranger. It is telling you that you have grasped a piece of the truth and are blind to the rest, and that the missing piece is hiding in plain sight. Newton's law was not simply broken by light. It was half illuminated by it, and the shadow where the other half should have been is the exact shape of everything Einstein would later discover. So this is not going to be a story about Newton being foolish, because he was anything but. It is going to be a story about how the most successful idea in the history of science could be profoundly right about almost everything, and still be built on a picture of reality that was, at its foundation, an illusion so convincing that it ruled physics for over 200 years, and still rules the inside of most of our heads today. To see how that illusion forms, and how light is the thing that finally shatters it, we have to understand exactly why the masslessness of light is the load-bearing wall of the whole mystery, and we have to be certain that wall is real. Now, you could imagine two ways out of a contradiction like this. The first would be to decide that one of the two things is simply false. Maybe light does have a little mass after all, some tiny amount that the equation could grab. Or maybe the bending is some kind of illusion, a trick of the atmosphere or the instruments. We will look hard at both of those escape routes, because they are exactly the doors a careful mind reaches for first, and it matters that we close them properly rather than just walking past them. But I will tell you now where this is heading, because the destination is stranger and more beautiful than either of those easy exits. Neither one is the answer, Light really does have no mass. The bending is completely real. Both things are true at once, and the only way for both of them to be true is for our entire picture of what gravity is to be wrong. Not a little wrong, not wrong in the third decimal place, wrong at the root. Wrong about the most basic question of all, the question a child asks when the pen drops to the floor. What is gravity, really? Because if gravity is a force that pulls on mass, then a massless beam of light is the one thing in the universe it should never be able to touch, and yet it touches it everywhere we look. The contradiction is not a puzzle to be solved with a clever adjustment. It is a crack, and if you follow the crack all the way down, the familiar idea of gravity as a force, an idea you have carried since before you can remember, quietly comes apart in your hands. This is the question we are going to sit inside tonight, and we are going to take it slowly, the way you would walk down a long staircase in the dark, one step at a time, feeling for the edge of each one before you trust your weight to it. The question sounds almost too simple to be dangerous. Light has no mass, so why does gravity bend it? But that small question is a doorway, and on the other side of it is one of the most complete reversals of common sense that human beings have ever been forced into. By the time we reach the bottom of the staircase, you are going to understand something genuinely unsettling. The light from those bent stars was never actually pulled off course at all. It went perfectly straight, the way light always goes, the way light cannot help going. It is the thing underneath the light, the thing you have always assumed was empty and flat and dependable, the very stage on which everything happens that turned out to be bent. But we are getting ahead of ourselves, and that is exactly the kind of leap I want us to earn rather than take. Before we can dismantle the idea of gravity as a force, we have to make absolutely sure of the one fact the whole paradox depends on. We have been saying it almost casually, the way you would mention the weather. Light has no mass. It is the load-bearing wall of this entire mystery, because if light turned out to have even a sliver of mass, the contradiction would soften, and Newton might quietly slip off the hook. So before we go any further, we need to ask the question properly, and we need to ask it the way a physicist would, which is to say suspiciously. How do we actually know that light weighs nothing at all? Not assume it, not take it on faith from a textbook. Know it. Because the answer to that question is far more precise and far more strange than the easy phrase we have been throwing around, and it shuts the first escape door so firmly that there is no reopening it. Part 2. The beam with no mass. When a physicist tells you that light has no mass, they are not making a casual statement, and they are not repeating something they read once and chose to believe. They are reporting the result of one of the most stubborn, most carefully checked measurements in all of science, a measurement that has been refined and tightened for over a century, and that has never once budged from the same answer. To understand why this matters so much, you have to understand what kind of claim it is. It is not a claim that light is very light, the way a feather is light. It is a claim that light has, precisely, no rest mass at all, and that turns out to be a statement loaded with consequences. Start with the word that does the quiet work in that sentence: rest. When physicists talk about the mass of a particle, they usually mean its rest mass, the mass it has when it is sitting still. And here we run into the first piece of strangeness, because light is never sitting still. It cannot. A beam of light always travels at the speed of light, that famous number, roughly 300,000 kilometers every second, and it travels at exactly that speed for everyone who measures it, no matter how fast they themselves are moving. You can never catch up to a beam of light, never slow it down, never find it at rest to weigh it. This is not a practical difficulty, like trying to weigh a hummingbird in flight. It is built into the deepest structure of reality, and it is connected to the masslessness in a way that is almost poetic. The reason light must always travel at the speed of light, and can never go slower, is precisely that it has no rest mass. The two facts are the same fact, seen from two sides. Anything with mass can always, in principle, be brought to rest, and can never quite reach the speed of light, no matter how much energy you pour into it. Anything without mass has no choice but to travel at that one speed, forever. Mass is what lets a thing slow down and stop. Light has none, so it never does. This already tells you that the masslessness of light is not some fragile, approximate thing that might crumble under closer inspection. It is woven into the fact that light moves the way it does. But physicists are not satisfied with elegant arguments. They want numbers, and they want limits, and they have spent enormous effort trying to catch light in the act of having even the tiniest scrap of mass. The logic of these experiments is clever. If a photon had even a vanishingly small mass, certain things would change in subtle, measurable ways. The behavior of magnetic fields around planets would shift slightly. Light of different colors traveling across the universe would arrive at fractionally different times, because with mass, different energies would travel at fractionally different speeds. The mathematics describing electricity and magnetism, which assumes a massless photon and works perfectly, would start to show small cracks. So physicists have measured the magnetic field of the Earth and of Jupiter with great care. They have timed the arrival of light and radio waves from distant cosmic explosions, and they have probed the behavior of electric fields in the laboratory, all hunting for the faintest sign of photon mass. They have never found one. Every experiment comes back consistent with zero. And because no experiment can ever prove a number is exactly zero, what these measurements give us instead is a ceiling, an upper limit, a statement of the form. If the photon has any mass at all, it must be smaller than this. And the ceiling they have established is almost comically low. The best limits place the possible mass of a photon at less than about 10 to the minus 18 electron volts, in the units physicists use for these things. You do not need to know exactly what that unit means to feel the weight of the comparison. An electron, itself one of the lightest particles known, is more than 1,000,000,000,000,000 times heavier than that ceiling. The photon's mass, if it has any at all, is squeezed into a space so small, so close to absolute nothing, that for every purpose in physics it is treated as exactly zero, and the theories that assume it is zero predict the world flawlessly. It is worth slowing down on how those ceilings are actually pulled out of the sky, because the methods are quietly beautiful and they show how seriously this has been checked. One of the cleanest tests rests on a strange fact. If the photon had even a sliver of mass, the familiar law that electric and magnetic forces weaken with the square of the distance would stop being exactly true. The force would fall off a tiny bit faster, with a built-in reach beyond which it faded away. So physicists have measured the shape of magnetic fields with extraordinary care, both in the laboratory and out in the solar system, where spacecraft have mapped the enormous magnetic field of Jupiter as they flew past. Any photon mass would have left a fingerprint in exactly how those fields thin out with distance, and none has ever appeared. The field falls off precisely as a massless photon demands. The second method is, to me, the more haunting of the two, because it uses the entire universe as the apparatus. If the photon had mass, then light of different colors would travel at very slightly different speeds, the lower energy light lagging a hair behind. Now imagine a sudden, violent flash somewhere far across the cosmos, a burst of radio waves or gamma rays from an event billions of light years away, all the colors leaving the source in the same instant. After a journey of billions of years, even the most microscopic difference in speed between the colors would have spread them out, so that the blue arrived noticeably before the red. We catch these flashes regularly now, and when we measure them, the colors arrive together, essentially in lockstep, after all that time and all that distance. That near-perfect simultaneity, stretched across the whole observable universe, slams the ceiling on the photon's mass down to almost nothing. The masslessness of light is not a textbook convenience. It is a fact written across billions of light years and confirmed every time a distant burst reaches us with its colors still holding hands. So the first escape door is now firmly shut, and I want you to feel it close. We cannot wriggle out of the paradox by saying that light secretly has a little mass that gravity could grab. It does not. The masslessness is not an approximation or a convenient assumption. It is one of the most precisely confirmed facts we have, checked across the magnetic fields of planets and the light of dying stars, and it holds. Light has no mass, and gravity bends it anyway. The contradiction is not going to soften. If anything, the more carefully we pin down the masslessness, the sharper the contradiction becomes, because we have removed the easy answer and left ourselves standing in front of the hard one. And here is where I want you to notice something about the shape of the problem, because it is going to guide everything that follows. We have two statements that both appear to be true. Light has no mass. Gravity bends light. And we have a law, Newton's law, that says these two statements cannot both be true, because gravity in that law acts only on mass. When you find yourself in a situation like that, with two solid observations and a law that forbids their coexistence, there is really only one place the error can be hiding. It is not in the observations. We have checked those to exhaustion. The error has to be in the law, or rather, in the picture of reality the law is built on. The picture of gravity as a force that reaches out and pulls on mass. That picture is about to be the thing that breaks. But before we break it, fairness demands that we give it its due, and in fact we are about to discover something that almost nobody expects. You might assume that Newton's physics is simply helpless here, that it predicts no bending at all and is flatly contradicted. The truth is far more interesting and far more revealing. If you treat light not as a wave, but as a stream of tiny particles, and you run those particles through Newton's gravity, honestly, all the way through, something remarkable happens. The mass that seemed to forbid any bending does not actually forbid it at all. It cancels itself out and leaves behind a prediction that light should bend after all. Newton's own physics, pushed far enough by people who were not afraid to take it seriously, predicts that gravity bends light. It gets the direction right. It even gets something close to the right size. And then it misses, by a factor that turns out to be the most important number in this entire story. To understand how Newton can be half right and half wrong at the very same time, we have to go back more than 2 centuries to a handful of people who dared to imagine light falling like a stone. Part 3. Newton's Secret Hedge. Isaac Newton was a stranger man than the tidy portraits suggest, and he was rarely as certain as the textbooks make him sound. He spent more of his life on alchemy and on private theology than on the physics that made him immortal, and even within physics he had a habit of posing questions at the edges of his own theories that he could not answer, almost as if he were leaving notes for someone who would come along later. One of those questions is the seed of everything we are talking about tonight. In the year 1704, in a book called Optics, Newton laid out his ideas about the nature of light, and he chose to end it not with conclusions, but with a long series of open questions he called queries. And in the very first query, the very first one, he asked this: do bodies act upon light at a distance, and by their action bend its rays? And is not this action strongest at the least distance? Sit with how astonishing that is. The man who gave the world the law that seems to forbid gravity from touching light is, in his own writing, wondering aloud whether massive bodies bend light, and whether they bend it most strongly when the light passes closest to them. That is, in plain language, gravitational lensing asked as a question more than 2 centuries before anyone could photograph it. Newton did not answer his own query. He left it hanging, but it tells us something important about how he saw light. Newton favoured the idea that light was made of tiny particles, little corpuscles, as he called them, streaming out from luminous bodies. And if light is made of particles, then a natural and almost irresistible question follows. If everything else made of particles falls under gravity, why not light? This is the thread that two later thinkers picked up and followed where Newton would not. The first was Henry Cavendish, one of the most brilliant and most painfully shy scientists who ever lived. A man so reclusive that he communicated with his own servants by written notes and left enormous amounts of his best work unpublished, discovered only long after his death. Sometime around 1784, Cavendish did the calculation. He took Newton's gravity seriously, treated light as a stream of fast-moving corpuscles, and worked out how much the sun's gravity would bend a ray of light grazing its surface. He got an answer, and then, being Cavendish, he told almost no one and filed it away among his papers. The second was a German astronomer and surveyor named Johann Georg von Soldner, who arrived at the same idea independently and, crucially, published it openly in the year 1801. Soldner worked through the same physics, light as corpuscles falling under Newtonian gravity, and he produced a specific, concrete number for the bending of starlight at the edge of the sun. That number was about 0.87 arcseconds. Now, an arcsecond is a tiny unit of angle. There are 60 arcseconds in an arc minute, and 60 arc minutes in a single degree, and 360 degrees all the way around the sky. So, 0.87 arcseconds is a staggeringly small angle, roughly the width of a coin seen from several kilometers away. It is far too small for the naked eye to detect, but it is not zero. And that is the point that should stop you. The Newtonian calculation, the one supposedly forbidden by the equation with mass in it, does not predict zero bending. It predicts a small but definite bend. So, how did the mass that should have shut everything down quietly disappear from the answer? The escape is one of the most beautiful tricks in all of physics, and it was sitting inside Newton's own work the whole time. It comes down to a coincidence so profound that it took another 200 years to understand why it is not a coincidence at all. In Newton's gravity, the force on an object grows with its mass. A heavier object feels a stronger pull. But there is a second law of Newton's, the famous one about force and acceleration, that says a heavier object is also harder to push, harder to get moving, more sluggish in response to any force. The technical word is inertia. And here is the magic. The mass that determines how strongly gravity pulls on an object is exactly the same number as the mass that determines how strongly the object resists being moved. So, when you ask how much an object actually accelerates under gravity, the mass appears once on the side that pulls and once on the side that resists, and the two cancel perfectly. The object's own mass drops completely out of the answer. This is why, in the old story, a feather and a cannonball dropped in a vacuum fall at exactly the same rate and hit the ground at exactly the same moment. The cannonball is pulled much harder, but it is also much harder to move, and those two effects cancel so precisely that the two objects fall in perfect step. The rate at which a thing falls does not depend on how much it weighs, and once you see that, you can see what happens to light. Even though the gravitational force on a nearly massless corpuscle of light would be tiny, its resistance to being moved would be tinier still, in exactly the same proportion, so the bending of its path does not vanish at all. The mass cancels, just as it does for the feather and the cannonball, and you are left with a bend that depends only on how close the light passes to the sun and how fast it is going. Run the numbers, and out comes Soldner's 0.87 arcseconds. This cancellation deserves more attention than it usually gets, because it is not really a lucky accident, and the fact that it looks like one was itself a clue that almost no one followed for 200 years. Newton needed two separate ideas of mass to build his physics. One is the mass that tells you how strongly gravity pulls on a thing, which we can call its gravitational mass. The other is the mass that tells you how stubbornly a thing resists being pushed, its inertia. There is no obvious reason in Newton's world why these two numbers should be the same. One is about gravity, the other is about motion in general, whether gravity is involved or not. And yet, every time anyone measured them, they came out identical to whatever precision the experiment could reach. Newton noticed this and could not explain it. He simply recorded that it was so. That quiet coincidence has been tested ever harder ever since, because physicists have a powerful instinct that when two numbers are always exactly equal, something is forcing them to be. Around the turn of the 20th century, a Hungarian named Roland Eötvös measured the equality of gravitational and inertial mass to extraordinary precision with a delicate twisting balance, and in recent years a satellite called Microscope checked it in the perfect free fall of orbit, confirming that different materials fall at identical rates to better than 1 part in 100 trillion. You can see the same truth in a famous piece of footage from the Moon, where an astronaut on the Apollo 15 mission in 1971 dropped a hammer and a feather together in the airless lunar vacuum, and the whole watching world saw them strike the dust at the same instant, exactly as Galileo had argued they must. This perfect equality, the thing Newton could only note and not explain, is precisely the loose thread that Einstein would pull, and when he pulled it, the entire idea of gravity as a force unravelled. So Newtonian physics, taken seriously and pushed honestly to its conclusion, does predict that gravity bends light. Newton hinted at it, Cavendish calculated it in secret, and Soldner published it. The old picture is not silent after all. It speaks, and it says, yes, light bends. And this is precisely what makes what came next so dramatic, because when the real measurement finally arrived, more than a century after Soldner, it did not match his number. It was almost exactly double. The starlight bent not by 0.87 arcseconds, but by 1.75. Newton's physics got the bending half right, and being half right, in this case, was the same as being completely wrong, because that missing factor of 2 was not a small error to be patched. It was the universe pointing at something Newton's world did not contain. To find out what, we have to follow a young man in a patent office as he has the single happiest thought of his life. Part 4. The Happiest Thought. In the year 1907, a young man sat at a desk in a patent office in Bern, Switzerland, and had an idea so simple that it sounds like nothing at all, and so profound that it would take him 8 more years to work out its full meaning. His name was Albert Einstein. He was not yet famous. He was a clerk evaluating patent applications, doing his real thinking in stolen moments. 2 years earlier, he had already published the work that would become known as special relativity, the work that fused space and time together and gave us the famous relationship between energy and mass. But gravity had not yet fit into that picture, and it nagged at him. Then, by his own account, came the thought he would later describe as the happiest of his life. It was this: a person falling freely does not feel their own weight. That is the entire idea. Picture someone who steps off a high platform and begins to fall. We tend to imagine that during the fall they feel the pull of gravity most intensely. Einstein realized the opposite is true. During the fall, they feel nothing. If they took coins out of their pocket and let them go, the coins would not drop away from them. They would hang there in the air beside them, falling at exactly the same rate, perfectly still relative to the falling person. In the falling frame, gravity has simply vanished. There is no up, no down, no weight, no pull. Everything floats together. This is exactly what astronauts experience aboard a spacecraft in orbit. We often say they are in zero gravity, But that is a misunderstanding. Gravity up there is nearly as strong as it is on the ground. That is what keeps them circling the Earth instead of flying off into space. They float not because gravity is absent, but because they are in continuous free fall, falling around the planet, and falling erases the sensation of weight, just as it did for the person stepping off the platform. Einstein took this small observation and turned it into a principle of enormous power. If falling makes gravity disappear, then there must be something fundamentally similar between gravity and motion. He sharpened it into a thought experiment about a sealed room. Imagine you wake up inside a closed box with no windows, and you feel your normal weight pressing your feet to the floor. There are two completely different stories that could explain what you feel, and Einstein's claim is that you could never, by any experiment performed inside that box, tell which one is true. In the first story, the box is sitting still on the surface of a planet, and what you feel is gravity. In the second story, the box is far out in empty space, with no planet anywhere near, and a rocket engine underneath is driving it forward, accelerating it faster and faster, and the floor is pressing up into your feet, the way the floor of an elevator presses up when it starts to rise. Gravity, or acceleration. From inside the box, Einstein said, they are indistinguishable. They are, in some fundamental sense, the same thing. This is called the equivalence principle, and the moment you accept it, it has a consequence for light that is impossible to avoid. Let me put you inside that box, because this is one of those ideas you have to feel in your body, not just follow on paper. You are sealed inside a windowless cabin, drifting somewhere in the emptiness between the stars. There is no planet anywhere near you, no gravity at all, and so you and everything loose in the cabin are floating, weightless, turning gently in the dark. Then, beneath your feet, the engines light. The floor begins to press up against your soles, softly at first, then steadily, and you settle down onto it, exactly as if you had been lowered onto solid ground. Your weight returns. It feels, in every way, like standing in your own kitchen. Now you reach up and clip a small laser pointer to the wall beside you, at the height of your shoulder, and you aim it dead level, perfectly horizontal, at the opposite wall a few steps away. You switch it on, and a thin red line crosses the cabin. But here is the thing. While the light was crossing the cabin was accelerating upward. By the time the beam reaches the far wall, the whole cabin, walls and floor and you has moved up just slightly. So the spot where the light lands is a hair lower than the height you aimed it from. To you, standing inside, the beam did not travel in a straight line at all. It curved gently downward, bending toward the floor, as if something were pulling it down. And now, spring Einstein's trap. You cannot tell, from inside this cabin, whether you are accelerating through empty space or standing still in gravity. The two situations are identical, that is the whole principle. So, if the light bends in the accelerating cabin, and the accelerating cabin is indistinguishable from a cabin sitting in gravity, then the light must bend in gravity too. It has to. There is no way for light to behave one way under acceleration and a different way under gravity, because nothing inside the box can tell those two apart. The bending of that red beam and the weight pressing into your feet are revealed as the same single fact, two faces of one thing. Notice what just happened, because it is the quiet hinge of this whole night. We predicted that gravity bends light, and at no point in the argument did we ask what the light is made of, or whether it has any mass. We did not need to. The bending came purely from the geometry of the situation, from the fact that the light takes time to cross the cabin, and the cabin moves in that time. Mass never entered the reasoning. Einstein had found a way to make gravity bend light that did not care in the slightest whether light had mass or not. There is one subtlety in the equivalence principle that we have to be honest about, because it is the very thing that points beyond it to something deeper. The equivalence between gravity and acceleration is only exact over a small region, a little box. Make the box big enough, and the disguise starts to slip. Picture not one falling person, but two, side by side, both released high above the Earth and falling toward its center. Because the Earth is a sphere, and they are each falling toward its middle, their paths are not quite parallel. They angle very slightly inward, so that as they fall, the two people drift almost imperceptibly closer together. An accelerating rocket in empty space would not do that. Inside a rocket, two floating objects stay exactly the same distance apart, because the floor pushes everything in one single direction. Real gravity, from a real planet, points toward a center, so it squeezes and stretches across any region large enough to notice. These are the tides, the same effect that raises the oceans toward the moon, and they are the telltale sign that distinguishes true gravity from mere acceleration. This matters enormously, because it tells us that gravity is not just acceleration in disguise everywhere. Locally, in a small box, it is. But across larger stretches, gravity reveals a structure that no simple acceleration can mimic, a pattern of squeezing and stretching that varies from place to place. And a pattern of stretching and squeezing that changes from point to point is exactly what we mean when we say a thing is curved. The equivalence principle gets Einstein to the door, showing that gravity must bend light. But the tides, the way real gravity refuses to be perfectly erased over large regions, are what told him that behind the door was not a force at all, but a curvature, a genuine bending of the space-time that everything, including light, has no choice but to follow. And that is the beginning of the escape from the paradox. The reason a massless beam can still bend is that the bending was never really about the light at all. But Einstein was not finished, and when he completed the picture 8 years later, the prediction he had reached in that patent office turned out to be only half the story, off by exactly the factor that Soldner had been off by, until one more ingredient was added, an ingredient that would finally separate his universe from Newton's forever. Part 5. The factor of 2 that broke Newton. When Einstein first put a number to the bending of starlight, he got the wrong answer. And the story of how he got it wrong, and then right, is the story of how a hair-thin angle in the sky came to decide the shape of reality. In 1911, working only from the equivalence principle and from the way gravity affects time, Einstein calculated that starlight grazing the sun should be deflected by about 0.87 arcseconds. If that number sounds familiar, it should. It is, almost exactly, Soldner's number. It is the Newtonian value. At that stage, in 1911, Einstein's new way of thinking about gravity made a prediction that was completely indistinguishable from the old corpuscle calculation of a century before. Had astronomers gone out and measured the bending then, and gotten that value, it would have confirmed both Newton and Einstein at once, and settled nothing about which picture of gravity was true. There is a remarkable near miss in history right here. There were attempts to test Einstein's 1911 prediction during eclipses in the following years, and, for various reasons, bad weather, the chaos of the First World War, a German expedition actually being detained in Russia, none of them succeeded. It is one of the luckiest failures in the history of science, because Einstein's 1911 number was wrong, and if it had been confirmed, it would have been a confirmation of a mistake. The near miss is even sharper than it first sounds. A German astronomer named Erwin Finlay Freundlich, one of Einstein's early champions, actually travelled to the Crimea in the summer of 1914, specifically to photograph an eclipse and measure the deflection that Einstein's 1911 theory predicted. He arrived with his equipment just as the First World War broke out, and because he was a German on Russian soil, he was promptly detained as an enemy alien, his instruments confiscated. The eclipse came and went with no measurement. At the time, it must have felt like a catastrophe, years of planning destroyed by the timing of a war. But that war saved Einstein from being right too early about the wrong number. By the time the skies were clear for measurement again, in 1919, the full theory existed, and the prediction had doubled to its correct value. History gave Einstein a second draft, and he used it. It is worth understanding, at least in feel, why the warping of time alone produces only half the bending. Light grazing the sun has a near edge, closer to the sun, and a far edge, farther away. Gravity slows time more strongly closer to the sun, so the part of the light wave nearest the sun is, in a sense, held back relative to the part farther out. A wave whose two sides advance at slightly different rates turns, the way a line of marchers wheels when those on one end take shorter steps. That turning, driven purely by the warping of time, gives the Newtonian half of the answer. The other half comes from the warping of space itself, the fact that the very distances the light crosses near the sun are stretched out compared to what flat space would give. The light has to thread through more space than a flat map would show, and that extra curved space bends its path by exactly the same amount again. Time bends it once, space bends it twice. Newton's universe has the first effect hiding inside it, and no room at all for the second, which is why it could only ever reach halfway to the truth. Between 1911 and 1915, Einstein was building the finished version of his theory, the one we now call general relativity, and in the process, he discovered that his earlier calculation had been missing something enormous. What it had been missing was the curvature of space itself. In the 1911 calculation, Einstein had accounted for the way gravity warps time, the way clocks run slower, closer to a massive body. That effect is real, and it contributes to the bending of light. But it is only half the picture. The full theory of general relativity revealed that mass and energy do not just warp time. They warp space as well, the three dimensions of length and width and height that we move through, and that warping of space adds a second, equal contribution to the bending of light. When Einstein redid the calculation in 1915 with the complete theory, including both the warping of time and the warping of space, the predicted bending doubled. It jumped from 0.87 arcseconds to 1.75 arcseconds, exactly twice the Newtonian value. I want to make sure the structure of this is clear, because it is the cleanest fingerprint in all of physics. The total bending of starlight by the sun comes in two equal halves. One half comes from the warping of time, and that half is the part that even the old Newtonian-style reasoning could capture, which is why Soldner and the 1911 Einstein both landed on it. The other half comes from the warping of space, and that half is entirely absent from Newton's universe, because in Newton's universe, space is just an empty, flat, unchanging stage on which things happen. Newton's space cannot curve, so Newton's physics could only ever get half the answer. It was not a little bit wrong. It was missing an entire dimension of the effect, missing the fact that space itself can bend, and the size of what it missed was not subtle. It was a full factor of 2, a doubling, the kind of discrepancy you cannot explain away as measurement error. This is why that tiny angle became the most important number in 20th century physics. The difference between Newton and Einstein was not philosophical hand-waving that could never be tested. It came down to a single, sharp, measurable prediction. If you measured the bending of starlight by the sun and got 0.87 arcseconds, Newton was right and space was flat. If you got 1.75 arcseconds, Newton was wrong, Einstein was right, and space itself was curved. There was no middle ground, no room for interpretation. One number meant a flat, dependable universe of the kind humanity had always assumed it lived in. The other number meant a universe where the ground beneath everything, the empty space we take for granted, was bent and shaped by the matter sitting in it. An entire worldview hung on whether a few stars near the edge of an eclipsed sun would appear shifted by one amount or by twice that amount. Stop and consider how strange it is that something so fundamental could turn on something so small. We are not talking about a dramatic, obvious effect. 1.75 arcseconds is a shift so slight that it is like noticing that a person standing 2 kilometers away has moved sideways by the width of a finger. To measure it at all, you would have to photograph stars right next to the blinding disk of the sun, which is impossible in normal daylight, and compare their positions to where those same stars sit in the night sky months later. You would need a total solar eclipse to blot out the sun, clear skies in some remote location along the narrow path of that eclipse, sensitive photographic equipment, and the patience to wait for the few minutes of darkness, and then months more for the comparison images. The whole future of our understanding of gravity, the question of whether space is flat or curved, came down to whether a team of astronomers could capture a handful of faint stars during a few minutes of eclipse and measure their positions to a precision finer than anyone had ever needed before. That measurement was coming. But before we stand on that cloudy island and watch it happen, we need to finish understanding the answer itself, because the factor of 2 has handed us the key, and we have not yet turned it. We now know that the bending of light comes from the curvature of space and time. But what does that actually mean? What is it, really, for space to be curved? And how does a curved space bend a beam of light that has no mass and feels no force? This is the center of everything, the place where the old idea of gravity finally falls away and something stranger takes its place, and it is worth walking into slowly. Part 6. Light goes straight through bent space. Here is the idea that everything has been building toward, and I am going to ask you to set down, just for a few minutes, the picture of gravity you have carried your whole life. The picture of gravity as a force, a pull, something reaching out across space to grab hold of things and drag them. I know how natural that picture feels, because you have felt it confirmed every time you have ever dropped something. But it is not what is happening, and the truth is stranger, and once you see it, far more elegant. Gravity is not a force that pulls on objects. Gravity is the shape of space and time, and objects are simply following that shape. Let me build this up carefully. In Einstein's universe, space and time are not a fixed, empty stage. They are more like a fabric, a flexible medium, and that fabric can be stretched and curved and warped. What does the warping? Mass and energy. Any concentration of mass or energy, a planet, a star, a beam of light, bends the fabric of space-time around it. A large mass like the sun bends it a great deal. A small mass bends it only slightly. The physicist John Wheeler captured the whole theory in a single sentence that is worth memorizing. Space-time tells matter how to move. Matter tells space-time how to curve. Those two halves are the entire engine. Matter curves the space-time around it, and that curved space-time then guides how everything else moves through it. Now, the crucial question, how does a thing move through curved space-time? And the answer is the most beautiful part of all. It moves in a straight line. It travels along the straightest possible path available to it. Not a path that has been bent by a force, but the path that is as straight can be, given the shape of the space it is in. Mathematicians have a name for the straightest possible path through a curved space. They call it a geodesic. And the reason this resolves everything is that a straight line through a curved space looks bent to anyone who imagines the space is flat. You already know an example of this, even if you have never thought of it this way. Imagine two travelers standing on the equator of the Earth, some distance apart, and both of them start walking due north, each one walking in what is, for them, a perfectly straight line. Neither one ever turns. Neither one steers toward the other. They simply walk straight ahead. And yet, as they walk, they get closer and closer together, until they meet at the North Pole. If you did not know the Earth was curved, you would swear some force had been pulling them toward each other, bending their paths inward. But there was no force. They each walked a perfectly straight line. It only looks like attraction because the surface they were walking on was curved. This is also why airplanes on long flights trace paths that look bent on a flat map, arcing up toward the pole instead of going straight across. They are not detouring. They are flying the straightest real path over a curved Earth, and it is the flat map that lies, not the plane. You have probably seen the popular image meant to show this, the one where space is drawn as a stretched rubber sheet with a heavy ball sitting in the middle, sinking into a dimple, and smaller balls rolling around the slope. It is a useful picture, but I want to warn you about it, because it quietly cheats in a way that hides the strangest part of the truth. The rubber sheet shows space being curved, a hollow that things roll into. But for slow-moving everyday objects, almost none of the falling you see is caused by the curving of space. Almost all of it is caused by the curving of time. This sounds impossible, so let me make it concrete. When you toss a ball across a room, its path arcs gently up and back down, and that arc looks like a very mild curve. But remember that the ball is also moving through time, and over the second or so of its flight, it travels an enormous distance through time, in the sense that light could cross hundreds of thousands of kilometers in that same second. The ball's path through space-time, through space and time together, is very nearly straight. It only looks curved to us because we squash that gigantic stretch of time down onto a small drawing of the room. What actually makes the ball come down is that time runs very slightly faster higher up, farther from the Earth, and very slightly slower lower down, nearer to it. The ball, following the straightest possible path through space-time, is steered by that difference in the flow of time, and the result is the familiar arc of a thrown object. This is the part the rubber sheet never shows, because a rubber sheet has no time in it. The deepest reason you fall when you trip is not that space is dented beneath you. It is that time itself ticks at different rates at your head and at your feet, and your body, trying to travel straight through a space-time where time is curved, gets turned toward the slower clocks, which always lie below you, toward the center of the Earth. Light is the one thing fast enough that the curvature of space matters as much as the curvature of time, which is exactly why light bends twice as much as the old time-only calculation predicted. For light, both halves of the geometry are in full play. Light near the sun is doing exactly this, except in the full 4 dimensions of space and time rather than on the 2-dimensional surface of a globe. The light is flying along a geodesic, the straightest possible path it can take. It never turns. Nothing pulls on it. It does the only thing light ever does, which is travel as straight as it is possible to travel. But the space-time it is traveling through has been curved by the mass of the sun, and so its perfectly straight path, when we look at it from far away and imagine that space is flat, appears to bend. The bending is real, in the sense that the light really does end up going a different direction than it would have without the sun. But the bending is not happening to the light. The bending is in the space. The light is innocent. It went straight the whole way. And now, finally, watch what happens to the paradox we started with. The reason a massless beam of light can bend just as a massive planet does is that the path, the geodesic, does not depend on the mass of the thing travelling along it. It is a property of the space, not of the traveller. Remember the feather and the cannonball, falling at exactly the same rate because the mass cancels out. This is the same fact, seen at its deepest level. Everything follows the same geodesics through curved spacetime, regardless of its mass, because the geometry does not care what is moving through it. It bends the road, and everything on the road follows the bend, whether it is a heavy planet or a weightless beam of light. The masslessness of light, which seemed to make the whole thing impossible, turns out to be completely irrelevant. Mass was never what gravity acted on. Mass was a red herring the whole time. This is the moment to say plainly what the title has been hinting at. The sentence "gravity bends light" is, in a precise sense, a lie. It smuggles in the old picture, the force reaching out, grabbing the beam, hauling it off course. None of that occurs. Gravity does not bend the light. Gravity bends the space, and the light goes straight through the bent space. The actor is innocent. It is the stage that is warped. And if you could somehow remove the sun's curvature while the light was mid-flight, the beam would not snap back to where Newton expected it, because it was never being held away from there. It was simply, always, going straight. I want you to sit with what this means about gravity itself, because it reaches far past beams of light. The weight you feel right now, holding you in your chair, the thing you have called a force your entire life, is not a force pulling you down. It is you trying to travel the straightest possible path through a space-time that the Earth has curved beneath you. The chair is the only thing interrupting that path, pushing up against you, which is why you can feel it. Let the chair vanish, and you would not be pulled down. You would simply fall freely along your geodesic and feel nothing at all, weightless, like the person stepping off the platform, like the astronaut in orbit. The most familiar sensation of your whole life, the press of your own weight, is not gravity gripping you. It is the shape of space-time, and you following it, in precisely the same way the starlight follows it past the sun. You and the bent beam are doing the same thing. You always have been. And once that lands, the universe is never quite the flat, dependable place you assumed it was when you walked into this. There is, however, a second way to understand why light cannot escape gravity, a way that comes at the same truth from a completely different direction, and it finally explains why the old equation was fooled by mass for so long. Part 7. Why energy falls when mass is zero. There is a second road into this truth, and I want to walk it with you because it explains a mystery we have not yet named. The mystery is this. If gravity was never really about mass, why did Newton's mass-based law work so well for 200 years? How did a law built on the wrong idea steer comets and find Neptune? The answer reveals something profound about what gravity actually responds to, and it shuts the door on the paradox from a completely different side. Go back to Newton's law one more time and look at what sits at its source. The thing that creates gravity, in Newton's picture, is mass. A massive object generates a gravitational field. The more massive, the stronger the field. Mass is the source. Now look at Einstein's theory, and you find that the source of gravity is something larger and more subtle. It is not mass alone. In general relativity, the thing that curves spacetime, the thing that generates gravity, is a bundle that physicists wrap up in a single mathematical object, and that bundle contains energy and momentum and pressure all together. Mass is in there, but only as one ingredient among several, and not even the most fundamental one. The real source of gravity is energy in all its forms. And here is where Einstein's earlier work comes back to close the circle. 2 years before the happiest thought, Einstein had already discovered the most famous relationship in all of physics, the one that says energy equals mass times the speed of light squared. People recite that equation constantly, but its real meaning is often missed. It does not just say that you can turn mass into energy, as in a nuclear reaction. It says something more sweeping. It says that mass and energy are the same thing, two names for one underlying quantity, interchangeable. Two currencies that trade at a fixed and enormous rate. Mass is simply energy that happens to be bound up and sitting still. A brick on a table has energy locked inside it, an immense amount, in the form of its mass. The energy and the mass are not two properties of the brick. They are one property, wearing two outfits. Once you understand that, the role of mass in gravity changes completely. If gravity responds to energy, and mass is just one form of energy, then of course massive things gravitate, because their mass is a great concentration of energy, but mass is not special. It is just the form energy usually takes in the everyday world. Look around you. Almost everything you can see, the walls, the furniture, your own body, is made of ordinary matter. And in ordinary matter, the overwhelming majority of the energy is locked up as rest mass. That is why, for centuries, it looked as though gravity cared about mass. In the world of slow, heavy, everyday objects, the energy and the mass are essentially the same number, so a law that tracks mass and a law that tracks energy give almost identical answers. Newton's law worked because, for planets and comets and falling apples, mass is a perfectly good stand-in for energy. The disguise held for 200 years because nobody had looked closely at something made of pure energy moving at the speed of light. But light is exactly that. A beam of light carries no rest mass, but it most certainly carries energy. This is not abstract. The warmth you feel on your face from sunlight is the energy of light being absorbed by your skin. The light from the sun carries enough energy and momentum that it exerts a real, measurable push on anything it strikes, a pressure, faint but genuine, which engineers are now using to drive spacecraft on solar sails, pushed across the solar system by nothing but sunlight falling on a thin reflective sheet. This is not a new suspicion either. 4 centuries ago, the astronomer Johannes Kepler noticed that the tails of comets always stream away from the sun, no matter which direction the comet is traveling, and he guessed that something in sunlight itself was pushing the tail outward. He was essentially right. Centuries later, the physics of light pressure was worked out properly, and it has since become real engineering. A Japanese spacecraft unfurled a great reflective sail in 2010 and rode the pressure of sunlight through space with no engine at all. And other missions have since done the same, sailing on light the way a boat sails on wind. So light is not some ghostly, weightless nothing that drifts past the world untouched. It carries momentum. It pushes. It can move a spacecraft. And anything that carries that much energy and momentum is something gravity must respond to, because energy and momentum are exactly what gravity answers to. There is one more turn of this screw that is worth naming, because it shows just how far the truth is from Newton's mass-based picture. In Einstein's theory, even pressure itself gravitates. The sheer outward push inside a hot, compressed gas adds, ever so slightly, to its gravity. This sounds almost absurd from the everyday point of view, where gravity is just about how heavy something is, but it has real consequences in the most extreme places in the universe, like the cores of collapsing stars, where the pressure becomes so enormous that its own gravitational pull helps drive the collapse further. Mass, energy, momentum, pressure, all of it bends space-time, all of it is part of the single source of gravity. Mass was only ever the most visible member of that family, the one we happen to notice first, because it is the form energy takes in the slow, cold, heavy world we live in. Light, made of pure energy racing at the universe's speed limit, simply belongs to a different branch of the same family, and gravity has never once treated it as a stranger. Light has energy. Light carries momentum, and in a universe where gravity responds to energy rather than to mass, light cannot possibly be exempt. It has the very thing gravity actually couples to. The masslessness, which seemed like an ironclad reason for light to ignore gravity, turns out to protect it from nothing, because mass was never the price of admission. Energy was, and light has paid it in full. So, we now have 2 complete answers to the question we started with, and they fit together like 2 halves of a single key. The first answer is geometric. Gravity is the curvature of space-time. Light follows the straightest path through that curvature, and the traveller's mass is irrelevant because the path belongs to the geometry. The second answer is about energy, Gravity responds not to mass, but to energy in all its forms. And light, though massless, brims with energy, so it both feels gravity and, in its own tiny way, creates it. These are not competing answers. They are the same truth told in two languages, and together they leave the original paradox with nowhere left to stand. Light has no mass, so what? Mass was never the point. It is worth lingering on how thoroughly this overturns the picture we started with, because the reversal is total. We began with the intuition that gravity reaches out and grabs hold of mass, and that a thing with no mass offers gravity nothing to grab. Both halves of that intuition have now collapsed. Gravity does not reach out and grab anything. It shapes the space-time that everything moves through. And the thing gravity responds to was never mass in the first place. It was energy, of which mass is only one familiar form. Two pillars of the original picture, the pulling and the mass, have both been quietly removed, and yet the bending of light remains more solid than ever, because it never depended on either of them. This is what it feels like when a scientific revolution actually lands. It is not that the old answers were tweaked. It is that the questions themselves turn out to have been built on assumptions that were never true. And once those assumptions fall away, the thing that looked like an impossible contradiction becomes the most natural thing in the world. Of course, light bends. It carries energy, it moves through space-time, and space-time is curved by everything in it. The only reason it ever seems strange is that we were looking at the universe through a picture that was wrong in exactly the places light could expose. Everything we have said so far, though, has been reasoning. Beautiful reasoning, careful reasoning, but reasoning all the same. Einstein could have been wrong. The equivalence principle is elegant. The geometry is elegant. The energy argument is elegant. And the history of science is littered with elegant ideas that turned out to be false. There was only one way to know whether the universe actually worked this way, and it required leaving the desk and the chalkboard behind, travelling to the ends of the earth, and pointing a camera at the sky during the few minutes when the moon hides the sun. The test was real, it was specific, and when it came, it did not arrive quietly. Part 8. The eclipse that crowned Einstein. To catch the sun bending starlight, you face a cruel, practical problem. The stars whose light bends most are the ones whose light passes closest to the sun, skimming right by its edge. But the sun is blindingly bright, and in its glare you cannot see any stars at all, let alone the faint ones nearly touching its rim. There is exactly one circumstance in which the sun's face is blotted out and the stars around it spring into view, a total solar eclipse, when the moon slides perfectly in front of the sun and, for a few short minutes, turns day into an eerie twilight. So the test of Einstein's theory, the test of whether space itself is curved, depended on chasing eclipses to remote corners of the world and praying for clear skies during the brief darkness. The man who took up this challenge was an English astronomer named Arthur Eddington, and his role in the story carries a weight beyond the science. The year was 1919. The First World War had just ended, a war that had set Britain and Germany against each other in 4 years of slaughter that consumed a generation of young men. Einstein was German, working in Berlin. Eddington was English. In the poisoned atmosphere after the war, there were those who felt that a British scientist had no business going to enormous trouble to test, and possibly to vindicate, the theory of an enemy national. Eddington, a Quaker and a pacifist who had refused to fight, saw it the opposite way. He saw a chance to prove that science stood above the hatreds of nations, that a truth discovered in Berlin could be confirmed by a telescope on a British expedition, and that knowledge belonged to all of humanity rather than to one flag. He organised 2 expeditions to observe the total eclipse of the 29th of May, 1919. One went to Sobral, in Brazil. Eddington himself sailed to a small island off the west coast of Africa called Principe. Let me take you there to that island on that morning because everything came down to a few minutes and a stretch of uncooperative sky. It is the morning of the 29th of May, 1919, on the island of Principe, and the weather is wrong. Eddington has hauled his telescopes and his fragile glass photographic plates thousands of miles by ship to this humid green island, and now, on the one morning that matters, the sky is full of cloud. A heavy rain falls in the hours before the eclipse. He can do nothing but wait, watching the grey ceiling overhead, knowing that the alignment of moon and sun he has travelled across the world to photograph will last only a handful of minutes and will not come again here for a lifetime. As the eclipse begins, the clouds still smother the sun. Then, slowly, maddeningly late, they begin to thin. Through gaps in the cloud, the darkened sun appears, ringed by the pale glow of its corona, and the sky around it has gone dark enough that a few stars are faintly visible right beside it. Eddington works the photographic plates as fast as his hands will move, the shutters clicking through the brief totality, capturing what little the clouds allow. He gets only a few usable plates. On most of them, the clouds have ruined everything. But on a couple, faint and trembling at the edge of visibility, there are stars, sitting just outside the positions where they belong. That night, and in the careful weeks that followed, Eddington measured those plates, comparing the positions of the stars near the eclipsed sun to their positions in photographs of the same patch of sky taken when the sun was elsewhere. The question was brutally simple. Had the stars shifted by 0.87 arcseconds Newton's value, or by 1.75 Einstein's? The measurement was agonizingly delicate, teasing out a shift smaller than a hair's width across the plate. And when the numbers settled, they came down on Einstein's side. The stars had moved by close to the larger amount, the amount that meant space itself was curved, the amount that Newton's flat universe could not produce. On the 6th of November, 1919, the results were announced at a joint meeting of the Royal Society and the Royal Astronomical Society in London. The president of the Royal Society, J.J. Thomson, who had himself discovered the electron, called it one of the greatest achievements in the history of human thought. And then the news escaped the meeting hall and ran around the world, and something happened that almost never happens in physics. It became a global sensation overnight. The next morning, newspapers carried the story across their front pages. Lights all askew in the heavens, one famous headline ran. The idea that a British expedition had confirmed the theory of a German scientist barely a year after the two nations had been at war struck people as something close to a miracle of reconciliation, a sign that the human capacity for understanding could outlast the human capacity for destruction. And Albert Einstein, who the day before had been known mainly to other physicists, woke up to find himself one of the most famous human beings alive, his name suddenly a synonym for genius, a status he would carry, half bewildered by it, for the rest of his life. There is a story from around this time that captures Einstein's own attitude better than any headline. Someone asked him what he would have done, what he would have thought, if the eclipse measurements had come back disagreeing with his theory. Einstein is said to have replied, with complete calm, that he would have been sorry for the dear Lord because the theory was correct. It sounds like arrogance, and maybe a little of it was, but it was really something else. The quiet confidence of a man who felt that the inner logic of his theory was so tight, so inevitable, that reality almost had no choice but to comply. He did not experience the eclipse as a nervous gamble that might destroy his life's work. He experienced it as the universe being asked, politely, to confirm what the mathematics had already made plain. It is worth being honest about the messiness behind the triumph too, because it has become a favourite target for those who want to claim the whole thing was rigged. The expeditions produced 3 sets of plates, Eddington's from Principe and 2 sets from Sobral, taken with 2 different telescopes. One of the Sobral telescopes gave results that landed beautifully on Einstein's value. The other Sobral instrument, which had apparently lost its focus in the heat of the day, gave a messier number closer to the Newtonian value, and that set was given less weight in the final analysis. Critics have pointed at this ever since, and whispered that Eddington simply kept the data he liked. But the honest answer is that the focus problem was a real, documented instrumental fault, and far more importantly, the experiment has since been repeated again and again over the following century, at eclipse after eclipse, and then with methods that need no eclipse at all. Each repetition has confirmed the Einstein value with greater and greater precision. Eddington's plates were the first word. Taken in difficult conditions with the tools of 1919, they were never the last word. The last word is overwhelming, and it says Einstein was right. What the eclipse confirmed was not just a number, it was an entirely new picture of reality. Space is not the flat, empty, indifferent backdrop everyone had always assumed. It is a flexible thing, curved by the matter within it, and that curvature steers the paths of everything that moves, including light. The measurement was tiny. Its meaning was not, and once astronomers understood that mass bends the light passing it, a thought occurred to them that would turn this delicate, hard-won effect into one of the most powerful tools in all of science. If a single star can nudge a passing beam, what could a whole galaxy do? What could 1,000 galaxies do? And could we use that bending deliberately to see? Part 9. When the bent beam became a telescope. The leap from a curiosity to an instrument is one of the most satisfying turns in this whole story, and it begins with the realization that a massive object does not bend just one ray of light. It bends all of them. Every ray streaming from whatever lies behind it gets bent as it passes, and if the geometry is right, those bent rays can be gathered and focused, exactly the way a glass lens gathers and focuses light. A mass, sitting in space, can act as a lens. Astronomers call it gravitational lensing, and it has become a way of seeing the most distant and the most hidden things in the universe. Einstein himself worked out the basic idea, though he nearly dismissed it. In 1936, prompted by a letter from an amateur scientist named Rudi Mandel, who had pestered him about the possibility, Einstein published a short paper describing how one star, lying directly behind another from our point of view, would have its light bent symmetrically all the way around the nearest star, producing a perfect ring of light. We call it an Einstein ring today. But Einstein, in that very paper, added a note of pessimism. He thought the effect would be far too small ever to observe, the alignment too precise, the stars too far apart. He published the idea, and in the same breath doubted anyone would ever see it. He was thinking too small. He was thinking of single stars. It was the astronomer Fritz Zwicky, a brilliant and famously combative scientist, who saw the real possibility just a year later, in 1937. Zwicky pointed out that you should not be thinking about single stars as lenses at all. You should be thinking about entire galaxies and clusters of galaxies, objects containing the mass of billions or trillions of stars. Such enormous concentrations of mass would bend light far more strongly, enough that the lensing might actually be seen. And Zwicky went further, with two predictions that were decades ahead of their time. He said that gravitational lensing could be used as a kind of natural telescope, magnifying distant objects we could not otherwise reach. And he said it could be used to weigh the lensing galaxies and clusters, to measure their total mass by how strongly they bent the light, including any mass that gave off no light at all. Hold on to that last point, because it is going to become the strangest and most important part of this entire story. For decades, these were just ideas on paper, because the instruments were not good enough to test them. Then, in 1979, it finally happened. 3 astronomers, Dennis Walsh, Robert Carswell, and Ray Wayman, were studying a distant quasar, one of those blazingly bright cores of an active galaxy in the early universe. And they found something strange. There appeared to be two quasars sitting very close together in the sky, and they were identical. The same spectrum, the same colors, the same fingerprint of light, as if someone had photographed one object twice. They had not found two quasars. They had found one quasar whose light was being split into two images by the gravity of a galaxy sitting between us and it. A galaxy bending the quasar's light around both sides of itself and sending two copies of it to our telescopes. It was the first gravitational lens ever observed, the famous twin quasar, and it confirmed that Zwicky had been right. Galaxies really do act as lenses. After that first discovery, the floodgates opened, and the images that have come since are some of the most extraordinary pictures astronomy has ever produced. There is the Einstein cross, where a single distant quasar appears as four separate images arranged in a cross around the galaxy that is lensing it, four copies of one object, conjured by the bending of its light. There are the great galaxy clusters, like the ones catalogued as Abell 2218 and Abell 370, where the light of galaxies far behind them is stretched into long, luminous, curving arcs that drape across the cluster like brushstrokes. There are very nearly complete Einstein rings, the exact phenomenon Einstein thought no one would ever see, now photographed in sharp detail by the Hubble Space Telescope and, more recently, by the James Webb Space Telescope, glowing circles of light from a single galaxy wrapped all the way around a perfectly aligned mass in front of it. Einstein doubted these would ever be observed. We now have galleries of them. And Zwicky's other prediction came true as well, the one about using lenses as natural telescopes. Astronomers now deliberately seek out massive galaxy clusters and point their best instruments through them, using the cluster's gravity to magnify the faint, distant galaxies behind it. The cluster acts as an enormous lens that nature has provided for free, boosting the light of objects so far away and so faint that no human-built telescope could see them unaided. Some of the most distant galaxies ever detected, galaxies whose light has travelled for almost the entire age of the universe to reach us, were found this way, their images brightened and enlarged by the bending of their light around a closer cluster. Lensing has even become a way of measuring the universe itself. When a single distant quasar is split into several images by a foreground galaxy, the light that forms each image has taken a slightly different route to reach us, and the different routes have different lengths, so the images are not perfectly in step. If the quasar flickers, the flicker shows up in one image first, and in the others a little later, sometimes days or weeks later. By timing those delays, astronomers can work backward to measure the actual scale and expansion rate of the universe, turning a lensed quasar into a kind of cosmic ruler. The bending of light, the thing that should not happen, has quietly become one of the tools we use to weigh the cosmos and clock its expansion. There is a gentler version of lensing too, that happens on the scale of single stars, and it has its own quiet power. When one star drifts almost exactly in front of another, far more distant star, the nearer star's gravity briefly focuses and brightens the light of the one behind it, a smooth swell of brightness that rises and falls over days or weeks as the alignment passes. Astronomers call this microlensing, and it has become a way of finding things that give off no light of their own. If the foreground star happens to have a planet, the planet adds a tiny extra blip to the smooth swell, and that blip betrays a world we could never have seen directly. Microlensing has revealed planets thousands of light years away, and even hints of rogue planets, worlds drifting alone through the galaxy with no star at all, detected only in the instant their gravity bent the light of a distant sun. Once again, the bending of light shows us the dark, the effect that Newton's law forbade. The effect that should have been impossible has become one of the sharpest eyes humanity possesses. Think about the journey this idea has taken. It began as a paradox that seemed to break physics, light bending when it had no mass to be bent. It became a delicate, almost impossible measurement during a clouded eclipse. And it has ended up as a standard, indispensable tool used every night at observatories around the world to weigh galaxies and to see across almost the entire universe. The contradiction in our title is not some embarrassing puzzle that physics would rather forget. It is, in practice, one of the most useful facts we know. But the most powerful use of all is also the most unsettling. And it takes us back to that prediction Zwicky made in 1937 about weighing the mass that gives off no light. Because when astronomers finally did that, when they used the bending of light to weigh the universe, the answer that came back was one that nobody was prepared for. Part 10. Weighing the invisible with light. When you use gravitational lensing to weigh a galaxy or a cluster, you are doing something that, when you stop to think about it, is almost miraculous. You are measuring how much an object's gravity bends the light passing it, and from that bending alone, you are calculating how much mass the object contains. You never have to see the mass. You do not need it to glow or to give off any light at all. You simply watch how it warps the light of things behind it, and the amount of warping tells you the amount of mass. The bending of light becomes a scale, a cosmic balance that can weigh things in total darkness. And this is the tool that led us to one of the most profound and disturbing discoveries in the history of science. When astronomers weighed galaxies and clusters this way, by the bending of light, and then compared that to how much mass they could account for by adding up all the visible matter, all the stars and the glowing gas and everything that shines, the two numbers did not match. They did not match by a little. The lensing consistently revealed far more mass than the visible matter could explain, by a factor of roughly 5 or 6. Galaxies and clusters bend light as though they contain 5 or 6 times more mass than anything we can see in them. There is something there, something heavy, something with real gravity that warps light exactly as mass should, and it emits no light of its own. It is dark. We have come to call it dark matter, and the bending of light is one of the primary ways we know it exists at all. I want you to feel the full strangeness of this, because it is easy to let a phrase like dark matter slide past as just another science term. What it actually means is this. The overwhelming majority of the matter in the universe, something like 5 times more than everything we can see, is a substance we have never directly observed. It does not shine. It does not block light. It does not, as far as we can tell, do much of anything except have mass and therefore gravity. We cannot see it. We cannot touch it. We do not know what it is made of, and our best detectors, built specifically to catch it, have so far come up empty. And yet we are confident it is there, in staggering quantities, woven through every galaxy, including our own. Why are we so confident? Because of how it bends light. The thing that has no mass, light, is the thing that reveals the existence of the thing we cannot see. We hold most of the matter in the universe in our understanding by a single thread, and that thread is the bending of a beam that, according to the old law, should never have bent at all. There is one demonstration of this so clean that it has become legendary, and it is worth picturing. It is called the bullet cluster, and it is the wreckage of a colossal collision between 2 clusters of galaxies that smashed through each other long ago. When 2 galaxy clusters collide, the visible matter, the hot gas that fills the space between the galaxies, slams together and slows down, piling up in the middle, glowing in X-rays, where it has been heated by the impact. So if visible matter were all there is, the mass of the system should sit where that gas is, in the center, where the collision was most violent. But astronomers measured where the mass actually is, using gravitational lensing, watching how the whole system bends the light of galaxies far behind it, and the mass was not in the center with the gas. The mass had sailed right on through. Most of the mass of each cluster was found out ahead, past the gas, exactly where a cloud of dark matter would be if it did not interact with anything, if it had simply passed through the collision like a ghost while the ordinary gas got stuck in the middle. The lensing showed the invisible mass in one place and the visible gas in another, pulled apart by the collision, caught in the act of being two different things. It is about as direct a fingerprint of dark matter as we have, and it was read entirely from the bending of light. The trail that led here is older than the lensing measurements, and it is worth knowing because it shows how many independent roads converge on the same strange conclusion. Back in 1933, the same Fritz Zwicky, who imagined galaxies as lenses, was studying a great swarm of galaxies called the Coma Cluster, measuring how fast the individual galaxies were moving within it. He found them moving so fast that the visible matter could not possibly hold the cluster together. By all rights, it should have flown apart long ago. Something unseen, he argued, must be supplying the extra gravity, and he gave it a name that translates as dark matter. For decades, almost no one took him seriously. Then, in the 1970s, the astronomer Vera Rubin measured how fast stars orbit within individual spiral galaxies and found the same impossible pattern. The outer stars moved far too quickly for the visible mass to explain, as though each galaxy were embedded in a much larger, invisible halo of gravity. The evidence kept arriving from different directions, and it kept saying the same thing. What gravitational lensing added was something the earlier methods could not provide: a direct map. The motions of galaxies and stars tell you that extra mass is present, but lensing lets you trace where it actually sits by reading the distortion it imprints on the light of everything behind it. Astronomers now survey huge patches of sky, measuring the subtle, systematic stretching of the shapes of millions of distant galaxies, and from that faint, coherent warping, they reconstruct the distribution of the unseen mass across enormous volumes of space. What emerges is a structure no eye will ever see directly, a sprawling web of dark matter threaded through the cosmos, with the visible galaxies strung along it like beads of light on invisible wire. The luminous universe, it turns out, is just the glowing decoration on a far larger scaffold we can perceive only through the bending of light. Take that one effect away, and most of the architecture of reality goes dark to us entirely. So consider where we have arrived. We started with what looked like a flaw in physics, a beam that bent when it should not. We followed it down through the equivalence principle and the curvature of space-time and saw that the bending was not a flaw at all, but a feature, a consequence of the true shape of gravity. We watched it become a tool, a way of seeing across the universe. And now we find that this same effect, this bending of massless light, is the main way we know that most of the universe is made of something we have never seen. The thing that seemed like the weakest point in our understanding turns out to be one of the strongest threads we have, and it is holding up most of reality. The bending of light is not a curiosity at the edge of physics. It is a lifeline running through the center of it. There is a kind of vertigo in that, if you let yourself feel it. Look up at the night sky. Everything you can see, every star, every band of the Milky Way, every distant smudge of a galaxy, is the small, glowing minority of what is actually out there. Surrounding all of it, outweighing all of it 5 or 6 times over, is a dark architecture you cannot see, mapped only by the way it bends the light of the things behind it. You are looking at a universe that is mostly invisible, and your only window onto the invisible part is the very effect that the most successful equation in the history of science said could not happen. The contradiction we opened with has become the thread by which we hold most of what exists. And we are not even at the most extreme expression of it yet, because there are places in the universe where gravity bends light so completely that it stops being a window and becomes a trap, places where the straightest possible line closes into a circle and then seals shut. Part 11. The black hole that closes the path. We have watched gravity bend light by a hair near the sun and bend it into rings and arcs around galaxies. Now we go to the place where the bending reaches its absolute limit, where space-time is curved so violently that light itself can no longer escape. We go to a black hole. And it is here, at the most extreme object in the universe, that the truth we have been building toward shows itself most nakedly, because at a black hole, the bending of light is taken all the way to its conclusion, and the conclusion is stranger than the trap it first appears to be. The closer light passes to a concentration of mass, the more sharply space-time is curved, and the more the light's path bends. Around a black hole, the curvature near the center becomes overwhelming, and there is a special distance from a black hole, at 1.5 times the radius of the boundary we call the event horizon, where something extraordinary happens. At that exact distance, space-time is curved so precisely that light can travel in a circle. A beam of light, aimed just right, will orbit the black hole, going around and around, the way a planet orbits a star, except that here it is pure light, looping endlessly. Physicists call this radius the photon sphere, the sphere at which light itself can be put into orbit. The mathematics that describes all of this was found with astonishing speed, and under circumstances that are hard to believe. Within only a few months of Einstein publishing his complete theory in late 1915, a German physicist named Karl Schwarzschild worked out the first exact solution of Einstein's equations for the space around a single concentrated mass. He did this while serving in the German army during the First World War, calculating the geometry of warped space-time from a military post on the Russian front between his duties. He sent his work to Einstein, who presented it on his behalf, and Einstein was reportedly surprised that such a clean, exact answer existed at all. Schwarzschild's solution contained, hidden inside it, the radius at which the curvature becomes so extreme that nothing can escape, the boundary we now call the event horizon, and the photon sphere just outside it. Schwarzschild himself did not live to see what he had found understood. He fell ill at the front and died only months later, in 1916. The geometry of black holes was first written down by a soldier in a war, and it has been confirmed, a century later, in the glowing rings the Event Horizon Telescope has photographed. For a long time, even Einstein doubted that such objects could really exist in nature. The event horizon seemed too strange, perhaps a mathematical artifact rather than a real place. It took decades of work by later physicists to establish that real stars, collapsing under their own gravity at the end of their lives, genuinely form these regions where the curvature seals itself shut. The name black hole did not even arrive until the 1960s, and the boundary itself is stranger than the popular image suggests. The event horizon is not a surface, not a wall of anything, not a membrane you could touch. It is simply the place where the bending of space-time becomes total, where every path that light could take, every direction it could be aimed, has been tilted inward. Nothing about it is solid. It is a one-way feature of the geometry itself, a frontier defined entirely by the behavior of straight lines, and an unlucky traveller crossing it would feel nothing special at the moment of crossing. No barrier, no jolt, only the slow, irreversible discovery that there is no longer any direction that leads back out. Let me bring you there, to the photon sphere, because standing at it would show you something about your own body that no mirror ever could. You are hovering on a platform at the photon sphere of a black hole, at the one distance where light can circle. Around you, the sky is distorted into something that has no name, the stars smeared and wrapped and multiplied by the curvature, the black disk of the hole yawning below you. You look straight ahead, level, along the direction of the orbit, and slowly you begin to understand what you are seeing in front of you. It is faint, and it is ringed, and it is the back of your own head. Light is leaving the back of your skull, travelling all the way around the black hole, along the circular path, and arriving back at your eyes from the front. You are seeing yourself from behind, carried all the way around by light that left you and came home. Then you tilt your gaze downward, inward, toward the black disk, past the event horizon, and you feel the geometry itself tilt with it. Every direction that used to mean away, every path that used to lead outward, has folded over to point inward. There is no longer any direction you could turn, any way you could aim a beam that leads back out. Out is simply not a direction that exists here anymore. That is the event horizon, and it is the ultimate expression of everything we have learned tonight. We say, a black hole traps light, that its gravity is so strong not even light can escape, and that is true as far as it goes. But notice how the old language sneaks the wrong picture back in. It makes it sound as though light tries to leave, and gravity, like a great hand, grabs it and drags it back. That is not what happens. Nothing pulls the light back in. The light, as always, travels the straightest possible path it can find, the only thing it ever does. It is just that, past the event horizon, the space-time is curved so completely that every straight path, every possible direction light could go, leads further in. The light is not being held against its will. It is going perfectly straight, as innocent as ever, and discovering that straight no longer has an exit. The trap is not a force. The trap is the shape of space, bent until out is gone. And this is no longer theory or thought experiment. We have photographed it. In April of 2019, an international project called the Event Horizon Telescope, which linked radio dishes across the entire planet into a single Earth-sized instrument, released the first direct image of a black hole, the one at the center of a galaxy called M87, 55 million light-years away. The image showed a ring of light surrounding a dark center. Then, in 2022, the same project imaged the black hole at the center of our own galaxy called Sagittarius A star. In both images, that bright ring is not some glowing structure attached to the black hole. It is light from hot gas swirling around the hole, bent by the black hole's gravity and wrapped around it so that we see it as a ring encircling the darkness. It is gravitational lensing carried to its ultimate extreme, the lens grown so powerful that it bends the light of the lamp around itself and presents it back to us as a halo around a shadow. When you look at those images, you are looking at a direct photograph of the answer to our question. You are seeing massless light bent into a ring by gravity, the title made visible, printed in radio waves gathered from across the whole Earth. So, let us draw the full arc of what gravity does to light, because we have seen it now at every scale, and it is all one thing. Near the Sun, gravity bends light by a hair, and that hair, measured during a clouded eclipse, overturned Newton's universe. Around galaxies and clusters, gravity bends light into rings and arcs and multiple images, and we use that bending to see across the cosmos and to weigh the dark matter we cannot otherwise find. And at a black hole, gravity bends light so completely that it can orbit in a circle, and past the horizon, every path light can take leads inward, and the bending becomes a one-way door. From the faintest deflection to the absolute trap, it is the same single fact, the same geometry, expressed with greater and greater intensity. Space-time is curved by mass and energy, and light, having no mass and needing none, simply follows the straightest line through whatever curvature it finds, whether that line is bent by a whisker, or closed into a circle, or sealed shut forever. And that brings us back, at the end, to the question we started with, and to the quiet lie that has been hiding inside it the whole time. Part 12. Light was never bent at all. We began with a contradiction that seemed to break physics. Light has no mass. Gravity, in the law we were all taught, acts only on mass, and yet gravity bends light everywhere we look. We have spent this whole journey resolving that contradiction, and now, at the end, I want to collapse it completely, because the resolution is not quite what even the careful version suggests. The deepest truth is stranger than gravity is strong enough to bend even light. The deepest truth is that the light was never bent at all. Think back over everything we have built. The light near the sun was not pulled off course by a force. It travelled the straightest possible path available to it, a geodesic, through a region of space-time that the sun had curved. The light wrapped around galaxies and clusters was not grabbed and steered. It went straight through space that billions of stars and an ocean of dark matter had warped. The light orbiting a black hole, looping all the way around, was not being whirled like a stone on a string. It was flying as straight as it is possible to fly, through a space so curved that the straight path closed into a circle. At every scale, from the faintest deflection to the event horizon itself, the light did exactly one thing, the only thing light ever does. It went straight. It was the space underneath it that bent. The bending we have been talking about all night, the bending in our very title, was never happening to the light. It was happening to the universe the light was crossing. This is why I have called the title a lie, and why the channel asked whether gravity lies. Gravity does not lie. The light does not lie. What lies is the picture in our heads, the old, intuitive, comforting picture of gravity as a force that reaches out and pulls, and of space as a flat, empty, dependable stage on which that force plays out. That picture is the falsehood. It is so deeply built into us that we hand it to children with a dropped pen, and it is wrong at the most basic level. There is no force pulling the pen down. There is no force pulling on the starlight. There is only the shape of space-time, curved by everything that has mass or energy, and everything else moving as straight as it can through that shape. The pen falls, and the starlight bends for the same reason, by the same mechanism, and that mechanism is geometry, not force. Once you have seen that, you cannot unsee it. The most familiar thing in your life, the weight that holds you in your chair, quietly changes meaning. You are not being pulled down. You are being held back by the chair from falling freely along the straightest path through a space-time the earth has bent beneath you. And here is the thing I find hardest to shake, the thought I want to leave you with as you drift tonight. You trust straight lines. We all do. The aim of a glance, the path of a beam of light from a thing to your eye, the simple confidence that when you look at a star, you are seeing it where it actually is. But the light from that star has crossed an entire universe to reach you, and along the way it has passed countless masses, each one curving the space it travelled through, each one bending its perfectly straight path by some small amount. The positions of the stars near the sun are not quite where they appear. The shapes of distant galaxies are subtly distorted by everything their light has passed. You have never, not once, seen the universe laid out exactly where it truly is. You have only ever seen it as the bent geometry of space delivered it to your eye, straight lines through a crooked cosmos, arriving already changed. And the largest part of what is out there, the dark matter that outweighs everything visible 5 or 6 times over, you cannot see at all, except by the way it bends the light of what lies behind it. This is not a flaw in the universe, and it is not a flaw in you. It is simply what it is to live inside a space-time that bends. The bending is not an obstacle laid between you and reality. It is part of the structure of reality, as fundamental as the light itself. And the questions it opens do not close. We still do not know what the dark matter is, the invisible mass we map only by the bent beam. We still cannot fully unite this beautiful theory of smooth, curving space-time with the strange, grainy quantum rules that govern everything small, which means that even now, even after all of this, we do not have the final account of why a particle of light responds to gravity at all. We have the shape of the answer, confirmed in 1,000 measurements, written across the sky in rings and arcs and the shadow of a black hole. And we have the honest, open edge of it, the part we have not finished, waiting in the dark. There is a quiet symmetry hiding in that unfinished edge, and it is a fitting place to rest. Gravity, in our best current guess at the missing quantum theory, would be carried by a particle of its own, the way light is carried by the photon, and that gravity particle, the graviton, is expected to be massless as well, travelling at exactly the speed of light. We have not detected it, and we may not for a very long time, if ever. But we got a beautiful hint that the picture hangs together in 2017, when two neutron stars collided more than 100 million light-years away. The collision sent out both a ripple in space-time itself, a gravitational wave, and a flash of light, and after journeying side by side across more than 100 million years of space, the ripple and the light arrived at Earth within about a second of each other. Gravity and light, it turns out, travel at the same speed, to a precision almost beyond belief, exactly as a theory of two massless messengers demands. The thing that bends the light and the light that gets bent move through the universe in perfect step. So hold that as the last thought before sleep. Light has no mass, and the deepest reason gravity still moves it is that gravity itself, at bottom, may be made of something just as massless, just as swift, woven into the same fabric. The beam and the bending are not two strangers, one acting on the other. They are kin, two expressions of a universe that is stranger and more seamless than the flat and solid world we imagined when we were children, watching a pen fall to the floor and being told, gently and wrongly, that a force had pulled it down. So the next time you stand outside on a clear night and look up, hold both of these at once. The light, reaching your eyes, is going perfectly straight, as it always has, as it cannot help but do. And the space it is crossing to reach you is bent gently and invisibly by everything that exists. Gravity does not lie. Your eyes do not lie. It is only the old idea of a flat, dependable, empty space that was never quite true, and the universe has been quietly correcting it in every beam of starlight that has ever reached you, already bent, already curved, already carrying the shape of everything it passed on the long way here.